No, yeah.
Okay, can you see this board?
Yes.
Yes, sir.
I think we derived the formula for diffraction, right? This is, I mean, for these angles, we will get high intensity when X-ray source and detector makes same angle from the lattice planes. This angle is theta, this is also theta. And obviously this theta is with respect to some plane, means some HKL plane. And this D is the corresponding intraplanar spacing. Okay. So if we have some other plane, our theta will change accordingly. All these things will change. So if we, if we, let us say we have some sample, we have some lattice structure inside the sample. We allow X-ray, let us say from theta is equal to some 5 degree to almost perpendicular to the sample, something like theta is equal to, let us say, 85 degree. So this X-ray source is moving clockwise. Correspondingly, the detector is also moving anti-clockwise. When X-ray source was making angle theta 5 degree, the detector was also making angle 5 degree. This is detector on this side. As X-ray source rotate clock, detector rotate anti-clock. When X-ray source was making 85 degree, detector was also making 85 degree. So at some angles, we will see constructive interference of waves. At some angles, we will see destructive interference. So what kind of pattern are we supposed to see? It is not as simple as we have seen in the case of optics. ये उतना simple looking नहीं होगा जितना आपने optics में देखा है. So we have theta here. We have intensity received on detector. In case of optics, we see this kind of graph. Right in the front of X-ray, we have maximum, and then we have the secondary maxima, third order, fourth order maxima on this side also. This is for one slit. But in this case, we have many slits. We have many orientation of slit also. Okay. So situation is very complicated here. What kind of graph do we see? Something like this. Almost zero intensity. Then at some angle, suddenly intensity increases. And it goes to a really high value. And then it very rapidly again come down. Then again becomes zero. At some other angle, you will again see some increase. Intensity can be anything. There is no order in the intensity. Then at some angle again, we will see some high intensity. Then again go down. So we have this kind of pattern. So let us say this angle is theta 1. This angle is theta 2. This angle is theta 3. Theta 4 and so on. Okay. Only one thing that we know is that we are getting constructive interference at these angles. इस ग्राफ को देख के सिर्फ आप इतना ही कह सकते हैं कि इन पर्टिकुलर एंगल्स पर कंस्ट्रक्टिव इंटरफेरेंस हो रहा है. Can we also say something about this interplanar spacing. Can we say anything about this order of diffraction? Can we say anything about type of lattice inside this crystal? क्या इंटरप्लेनर स्पेसिंग को लेकर, प्लेन के ओरिएंटेशन को लेकर, ऑर्डर ऑफ डिफ्रैक्शन या लैटिस के टाइप जैसी कोई इंफॉर्मेशन इस ग्राफ से आपको मिल सकती है?
सर प्लेन की तो एटलीस्ट मिलनी चाहिए आई थिंक.
So now we have to apply some trick, some hit and try to get all the relevant data from here. Okay, कुछ ट्रिक, कुछ टेक्निक लगा करके इसी से डेटा रिट्रीव करना होगा. So what is that trick? Trick is something like this. We do not know what kind of lattice does it have. We have no idea whether this lattice is simple cubic, whether it is BCC, FCC. We have no idea, right? We also do not know which peak represent which D. हमें ये भी नहीं पता कौन सी peak किस plane को correspond करती है. But still we can get many relevant things from this graph. Let us assume that we have simple cubic lattice. मान लेते हैं कि simple cubic lattice है. If that is true, then what is interplanar spacing? D is equal to, for some HKL plane, A upon okay. Can you please tell me what is maximum possible D here? Maximum D means minimum of H square plus K square plus L square. What is the minimum possible value of this summation?
3 or 0.
Like you put H1, K0, K0, or you can choose 0, 1, 0. This is the minimal set, right? In all these three cases, what is this summation? 1 only, right? So what is the maximum value of D in this case? A.
1.
HKL, this square root is 1, so D is equal to A. What about second maximum? So D decreases.
A by root 2.
D is decreasing in this direction. So first entry is the maximum value. For second entry, what can we have? Let us take H is equal to 1. Let us take K is also 1, 0, or this, or this. In all these cases, this summation is equal to how much? 2 only. What is D? A by root 2. Okay. Or something like this. Similarly, next D will be A upon root 3. And what is the next possibility? So for this, we have H square plus K square plus L square is equal to 3. What is the next possible summation? We can also get 4. How do we get 4? Something like 2, 0, 0. Can we have any other form? I think no, right? So these planes will give us A by 2. Okay. What is the angle of reflection for D is equal to A? Let me call it D1. If we put this D is equal to A in this formula, let us put n is equal to 1. अभी आप n को 1 ले लीजिए. We take first order. So for first order, we can calculate at which angle we will see reflection from 100 plane. Okay. Let me call that angle theta1. If I put d is equal to ay root 2, I will get those angles which will reflect from 110, 101 or 011 plane. Let me call that angles theta2. The planes, I mean the angles which shows light reflected from 111 plane are theta3 and theta4 and so on. Okay. So I have a collection of thetas for simple cubic, right? For a simple cubic lattice, I know that I should get peaks at these angles. Okay. Obviously it depends on A. इसमें A अभी भी रहेगा, right? Like n here, n lambda here, 2. D is equal to some constant times A. किसी constant के साथ A multiplied है. 1 into A, 1 by root 2 times A. So yes, it depends on A. It depends on lambda. Okay. So lambda is known. Lambda वैसे पता है. So all these angles are function of wavelength, lattice parameter. Okay. And if I calculate their ratio, यदि मैं इनका ratio calculate करूँ तो now this is some fixed number. ये किसी पे depend नहीं करेगा. It does not depend on lambda. It does not depend on A also. Let me show you. What is theta 100? So sine theta 100 is equal to
D by 2 lambda or something.
so sine theta is 1
Okay.
n is
Lambda
1
by 2.
lambda upon 2 d 100 means only A.
Yeah.
Sine of theta 110 is lambda upon 2 d means A by root 2. Okay. Sine theta 111 is equal to lambda root 3 upon 2A. What is the ratio of sine theta 100, sine theta 110, sine theta 111?
1 is to root 2 is to root 3.
So it is a constant, right? It does not depend on lambda, it does not depend on A also.
Right. So
Sir,
Yes.
sir, n equals to 1 means?
First order diffraction. So
No, sir.
for the same plane, for the same set of plane, you can get many angles which will show constructive interference. I mean, even the 100 plane can have many thetas where you will get constructive interference. Okay. Similarly, 110 planes can have many angles which show you maximum intensity. So we are just looking at first value, the smallest theta, where I will get the high intensity. At second order, theta will increase, I will get second value.
Sir, in interference, n equals to 1 means close to the center of the screen, no, sir. Like that, here, any connection is there?
There is
N
no
equal-
center here, right?
like theta equals to 90, it is center for 0 and 180 degrees.
Actually, there is no concept of center now. So, I mean, I think you cannot map from there.
Sure. Okay, sir.
In fact, there is no center in this graph also. There is no symmetry in this graph. This peak can be anywhere, depending on the sample you are using. Or I can say that this ratio is the characteristic property of simple cubic. I mean, what are the numbers here? Like 1 by 2, root 2 by 2, root 3 by 2. So I can say this ratio, if I get this ratio in thetas, I can say my lattice is simple cubic. Similarly, calculate the same thing for BCC. I will get some other answers. I will get something like some constant C1 colon C2 colon C3 for BCC. We will have to do full calculation. पूरा calculation दोबारा से करना पड़ेगा. We will get similar concept for some FCC crystal. Okay. Now we have some unknown graph. What do we need to do? Note down these angles, theta 1, theta 2, theta 3. Calculate their sign, calculate their ratio, and try to,
So,
yes,
sir, in case of other cubic lattices, not cubic, other lattices, we need to change only A, right? Or HKL.
see, this formula is only for simple cubic, right?
Okay.
So calculation is extremely non-trivial, extremely difficult for other cases also. Okay. So it's a difficult exercise to find similar numbers for other unit cells also. But it is
So
doable.
just for an example, what will be the formula for BCC or FCC, any one of them?
So first of all, there are two problems. When we drive this DHKL or whatever, we prefer to choose primitive unit cell. Primitive means the effective numbers of point in unit cell are 1. So BCC is actually a conventional unit cell. We have to find the primitive version of this unit cell. Do you know what is the primitive version of BCC unit cell? Let me show you. It's not very easy to draw, but let me still try. So these are the three axes. Okay. I am going to make one unit cell on this side, conventional BCC cell. Which plane does it belong to? ये किस region में है? Here X is positive, Y is positive in this region, Z is negative in this region. Okay. I am going to draw one unit cell, and this is the body centered point. Let me draw one unit cell in this plane. I mean, this unit cell belong to which region? X is negative here, Y is positive here, Z is positive here. This is the corresponding body centered point. Let me draw one unit cell in this region. What is this region? X is positive here, Y is negative here, Z is positive here. This is the corresponding body centered point. The primitive unit cell of BCC is this. Let me draw with some other color. Connect this origin to this body centered point. Connect this origin to this body centered point. Connect this origin to this body centered point. Using these three vectors, make a cube. And these vectors are not perpendicular. ये जो black color से line खींची गई है, ये perpendicular नहीं है एक दूसरे पे. Make a cube using these three vectors. It is some kind of deformed cube. Make unit cell from these vectors. That will be primitive cell of BCC. Okay. So BCC cell look like this. I mean, it is some kind of deformed version of unit cell. Sorry. So angles are not 90 here. यहाँ पे जो angles है 90 degree नहीं है. So what is the corresponding interplanar spacing? Obviously this formula will not work. ये formula कब काम कर रहा है? When all these three vectors are perpendicular to each other. So this formula will also get modified. ये formula भी modify होगा. Accordingly, this whole calculation will get modified, and we will
Sir,
get some other set. Yes,
it's like parallel or piped, sir.
something like that. Yes.
Okay.
So the interplanar spacing will also change accordingly. So use this new interplanar spacing, use that new formula, again calculate all these things. So this is a difficult calculation, but this is one-time calculation. So softwares are available. You just give them this graph. आप उनको सिर्फ experimental data दीजिए. They do everything on their own because they have full database of all unit cells. जितने भी possible unit cells हैं सभी का database उनसे पहले से होता है. It calculate this ratio, try to match this ratio with the experimental data, and it can easily tell you what kind of lattice are there in this unknown sample. आपका जो sample है उसमें कौन सा lattice है, you will get to know. So technique is verify ratio of angles. It should match with one of the possible unit cell, and from there you will get the answer. Now once you know that this is simple cubic, this is the first angle, okay, you can also calculate which plane does it belong to, and now you can directly again apply this formula. N lambda is equal to 2d sin theta. Put that value of theta here, you will also get interplanar spacing or lattice parameter. जब आपको पता चल गया कौन सा क्यूब कौन सा सिस्टम है ये, just put d here, you put theta here, this formula will tell you what is the lattice parameter, what is the gap between the planes. So that's how we use both theory and experimental data together to get the meaningful output. Let me show you some real XRD patterns. You can see on net. You get peaks like this, something like this. Can you see any order? There is no order in
No, sir.
intensities. This dark bottom line is the noise in the data. जो सबसे नीचे आप देख रहे हैं fluctuations, ये noise है. But at some point, you are seeing extremely sharp peaks. One thumb rule is that intensity also depends on order. First order में intensity ज़्यादा मिलेगा, second में कम, third में और कम. Okay. There is this physics behind the broadening of peak also. जो peak में broadening हो रहा है, इसका भी अपना एक physics है. We will not discuss that. This tells you in how much range your crystal is uniform. आप जो physics पढ़ रहे हैं, आप crystalline solid पढ़ रहे हैं, right? But no crystal is perfectly crystalline. कोई भी solid पूरी तरह से crystal नहीं होता है. After some distance, this ordering of crystals automatically break. कोई deformation आ जाएगा, कोई impurity आ जाएगी, कुछ होगा, पर crystal structure break हो ही जाता है. Something like this. We have some sort of deformation. This broadening in peak tells us what is the size of one single crystal. एक crystal का size on an average कितना है? एक जितना कम width का होगा, we have bigger crystals in that sample. Peak की broadening ज़्यादा होगी, means we have a smaller crystal in that sample. So in all the research where we use material, X-ray diffraction is the first step which we have to pass. यदि आप मटेरियल से रिलेटेड कोई भी रिसर्च कर रहे हैं, आप कुछ भी बना रहे हैं, यू मे बी ट्राइंग टू मेक सम हाई एनर्जी डेंसिटी बैटरीज, आप हो सकता है बैटरी बनाने की कोशिश करें, और यू आर ट्राइंग टू मेक एनी मटेरियल विच डज नॉट डिसइंटीग्रेट इजली, whatever you are trying to make, XRD tells you whether you have made the same thing or not. XRD बताता है कि जो आप बनाना चाहते थे वही बना है या कुछ और बन गया है. For example, let us say you are trying to mix zinc and copper. You learn something from chemistry, and you are trying to conduct database. But before zinc and copper react, zinc और copper react करते उससे पहले zinc reacted with oxygen in the environment and it makes zinc oxide. आप कोशिश कर रहे थे जिंक और कॉपर को रिएक्ट कराने की, रिएक्ट क्या कर गया, जिंक ऑक्साइड एंड कॉपर, एंड यू विल गेट समथिंग व्हिच यू डू नॉट वांट. आपको कुछ ऐसा मिलेगा जो आप चाहते ही नहीं है. बट हाउ विल यू कंफर्म वेदर what exactly is in your sample? Same thing which you wanted or the thing which you do not want? कैसे पता चलेगा वही मिला जो आप चाह रहे थे या कुछ और बन गया है? This tells you. Make zinc oxide plus copper, take XRD, use it as a reference graph. Now try to make your sample, check it with the reference graph. If you are getting the same thing, then it means you got which you do not want. आपको वो मिला जो आप नहीं चाहते थे. If there is no peak of oxygen, then you have got your desired sample. ऑक्सीजन की पीक आपको नहीं मिल रही है, it means आपको वही मिला है, वही बना है जो आप बनाना चाह रहे थे. That is why XRD is so important. Almost all institute have XRD. We have one in our campus also. आपके MNIT के संस्थान में भी एक XRD मशीन है. So whenever you come back in campus, you can ask Dr. Naresh Kumar to show you XRD machine. जो डिपार्टमेंट के हेड हैं डॉक्टर नरेश कुमार, आप उनसे रिक्वेस्ट कर सकते हैं, he can show you. So this is all about this X-ray diffractometry. So how do we generate X-ray? X-ray generate करने का क्या टेक्निक है? We have a Coolidge tube in which we generate some high energy electrons. And how do we generate high energy electrons? We heat a filament to get some free electron. Once we get free electron, we pass them through some electric field in this direction.
Sir, can we pass through cyclotron?
Cyclotron also has the same function. They go through some electric field, and in that process their speed increases. There is only one way to increase the speed: apply some force. That's a Newton's law. If you want to change the speed, it is proportional to force. So apply some force. And what force do we apply on electrons? Obviously it is electric force, so we have to apply some electric field to them. And how do we apply this electric field? By using two electrodes and applying some extremely high potential between these electrodes. So we have a battery of the order of, let us say, 10 kilovolt or something like that. So when we apply such a strong electric field, we get electrons of extremely high energy, and these high energy electrons hit a target of heavy atoms, and once they hit this target, we get some electromagnetic radiation out from this target, and these are called X-rays. What is the wavelength of this X-rays? Of the order of angstrom, nearly 10 angstrom or so. Okay, 10 angstrom to 100 angstrom, something like that. So first thing, दिस इज नॉट मोनोक्रोमेटिक. ये ऐसा नहीं है कि यहाँ से सिर्फ एक ही वेवलेंथ निकलेगा. We get a mixture of wavelengths in this process, and this mixture is not uniformly distributed. Means if I plot wavelength versus intensity corresponding to a particular wavelength, lambda versus intensity of wavelength, I get a graph like this. This is at some potential B is equal to V1. आपने कुछ बैटरी पे, let us say you applied 10,000 volt, and we get a graph like this. If I increase the potential, I mean if I increase the electric field, or if I apply more, if I give more and more energy to electrons, this graph is modified. Modify होके कैसा बनेगा? Something like this. So this is for some other potential, and B2 is greater than B1. Not only this, at some points we get sharp spikes, like, so it is a kind of discontinuity that intensity suddenly increase for some particular wavelength. It look like that we have one more source of these particular wavelength. आप कह सकते हैं कि कोई और भी सोर्स है जहां से इस तरह की वेवलेंथ जनरेट हो रही है. And these spikes for B is equal to B2 also इस पर भी मिलेंगे. And their position does not change. इनका पोजीशन भी फिक्स है. These positions change only if you change the material. यदि आप जो टारगेट यूज किया है उसको बदल देंगे, then only it will change. Otherwise these spikes do not change. So you can see this profile have two types of spectra. One is this continuous variation. एक तो आप देख रहे हैं continuously intensity vary करती है. This is called continuous spectra. And on this continuous spectra, we see some discrete spikes. And these spikes does not depend on the electrons, it does not depend on the battery, it only depends on this target atom. Or you can say these are the properties of the target atom, or these are the characteristics of material only, and therefore it is called characteristic spectra. And these two together make X-ray spectra. So we have two questions. Source of continuous. I mean, why do we get such a curve? ये curve कहाँ से आ रहा है, क्यों आ रहा है? Second question is source of characteristic spectra. Why do we get these peaks? ये peaks कहाँ से आ रही हैं? So let us discuss these two things one by one. And in order to understand these behavior, ये behavior को समझने के लिए, we need to know what is going on when electron hit this target. क्या होता है जब इलेक्ट्रॉन इस टारगेट को हिट कर रहे हैं? देयर आर टू पॉसिबिलिटीज, यहाँ दो तरह की पॉसिबिलिटीज है. So this is the positive core, positive nucleus of target atoms, and around this positive nucleus many electrons are moving in their respective cells. इस एटम के सेल न्यूक्लियस के अराउंड इलेक्ट्रॉन्स अपनी अपनी सेल में मूव कर रहे हैं. So we have these electrons. Okay. And we have electrons coming from some electron gun at a very high speed. बहुत स्पीड से आते हैं ये, and they hit this target. इस टारगेट को हिट कर रहे हैं. When they come close to this electron cloud, they have some initial speed, and this speed is quite high. They can enter into this cloud. इस cloud में अंदर चले जाएंगे. But at the same time, they are also getting some force from this cloud. इस cloud से इनको बाहर की तरफ में force भी लगता है, right? So what will happen in this process? क्या होगा? They will enter into this cloud, but their speed will decrease. जैसे जैसे क्लाउड में अंदर बढ़ते जाएंगे, इनका स्पीड कम होगा. Okay. और you can say that this high speed electrons deaccelerate in the electron cloud. And when an electron accelerate or deaccelerate, क्या होता है? जब कोई इलेक्ट्रॉन का स्पीड चेंज होता है, वो इलेक्ट्रोमैग्नेटिक वेव के फॉर्म में रेडिएट करता है.
सर ये लास्ट लाइन फिर से रिपीट कर देंगे?
See, whenever a electron accelerate or deaccelerate, जब भी कोई चार्ज पार्टिकल को आप एक्सेलरेट करेंगे या डिएक्सेलरेट करेंगे, इट एमिट्स रेडिएशन. उसमें से रेडिएशन निकलेगा. That's a fundamental thing. इसका सोर्स हम डिस्कस नहीं करेंगे. ये एक फंडामेंटल प्रॉपर्टीज है चार्ज पार्टिकल्स की. दिस इज एवरीवेयर ट्रू. ये हर जगह ही सही है.
Sir, this is true for just electron or any particle?
Any charge particle.
Okay. Sir.
You may ask what happens to these electrons. जो electrons atoms में move कर रहे हैं, ये भी तो accelerate कर रहे हैं. Speed is not changing, but their velocity is changing, right?
Yes, sir.
So what happens to it? Don't they
Sir,
radiate?
can we say that this is a minute change?
No. In fact, इसी के पीछे तो पूरा संग्राम हुआ है. When Bohr gave atomic model, scientists asked Bohr that why electron do not radiate their energy. क्या ऐसा खास है कि इस मॉडल में, what is the model given by Bohr? Electrons are moving around a positive nucleus. And why did not scientists accept this theory? इसको accept ना करने का क्या reason था? If electron is moving on a circle, it will radiate. If it radiate, it will lose its energy. If it lose its energy, with time, this electron will fall into the nucleus. Then Bohr said that this is true, but for some particular orbits, this phenomena does not happen. कुछ particular orbit के लिए ये phenomena नहीं होगा. क्या है वो orbit? For those orbit, we have this relation. ये relation कहाँ से आया? उस टाइम कोई जवाब नहीं था इसका। क्यों इन ऑर्बिट्स के लिए नहीं होगा, इसका भी कोई जवाब नहीं था। Now we have answers to all these problems, but answers are quite complicated. Answers हैं अब क्यों इलेक्ट्रॉन रेडिएट नहीं करता है, but these answers are somewhat complicated, उनमें हम नहीं जाएंगे अभी।
Sir, de Broglie answered this, no sir.
Yes, see, de Broglie give you answer in some sense, but I mean, see, de Broglie has nothing to do with radiation. De Broglie radiation वाले part को लेके अभी भी कुछ नहीं कहा है. In fact, de Broglie have nothing to do with charge. De Broglie का charge से कोई connection ही नहीं है, right?
Yes sir.
So these are something which you may learn if you continue in physics at some time. Otherwise, there are many things in physics which are very strange. So this is a fundamental thing that any charged particle radiates when you accelerate it or decelerate it. So in this process, some energy comes out. So this will decelerate and it may change its path, whatever it is doing. But in this process, you are getting some energy out. This energy is X-ray. How much is the wavelength of this energy? Sorry, how much is the wavelength of this X-ray? If X-ray has energy E, wavelength has to be hc upon lambda. How much is E? It is a difference of E naught. E naught means initial energy of electron, जिस energy से वो अंदर गए थे, minus E1. E1 means final energy of electron when they come out from the atoms. So this much energy is lost by the electrons, and this energy is received as X-ray, and we have correspondingly some wavelength. What is E naught minus E1? E naught minus E1 कितना होगा? E naught is fixed. E naught हमने बनाया है. How much is E naught? If we pass one electron in a potential of V volt, how much energy have we provided it? हमने उसको कितना energy दे दिया?
EV.
What about E1? E1 we do not know. It depends on how does this electron interact with the atom. इसके साथ कैसे interact करेगा उस पर depend करता है. So E1 can have any range. E1 की कोई भी range हो सकती है. E1 can be 0 also. Means electron lost all its energy. Electron अपनी सारी energy lost कर दी. और E1 is equal to EV also. Electron interact ही नहीं किया, ऐसे ही वैसे ही चला गया. What is the corresponding wavelength? So we have some minimum estimate. What is the minimum value of lambda? E naught. I mean the maximum difference. What is the maximum value of lambda? Or lambda is equal to infinity. So these are the bounds on the lambda. Lambda कम से कम इतना होगा, ज़्यादा से ज़्यादा इतना हो सकता है. So what is lambda minimum? This is EV. Lambda minimum is this, hc upon EV. And that is why when we increase the potential, the minimum wavelength decreases. यही वजह है कि जब आपने पोटेंशियल बढ़ाया, मिनिमम वेवलेंथ कम हो गया. So this is hc upon EV1. This is hc upon EV2. Since V2 is greater than V1, lambda 2 is smaller than lambda 1. What about on right hand side? Theoretically it should go to infinity. Theoretically तो infinity तक जाना चाहिए, but it ends at some point. There is no drastic end. Okay. So this is the origin of continuous spectra. What about characteristic? I mean, why do we get these peaks? ये peaks कहाँ से आ रहे हैं? There is another phenomena happening in this atom. What is that? These electrons.
Excitation of the atom.
Yes. So these high energy electrons enter into this electron cloud, and these electrons are so energetic that even after deacceleration, they still have enough energy to kick out these electrons from their cell. इनमें अभी भी इतना एनर्जी है कि ये जो ऑर्बिट के इलेक्ट्रॉन्स हैं इनको किक करके बाहर निकाल सकते हैं. Okay? Or in other words, these high energy electron can make this atom unstable for a moment. कुछ समय के लिए इस एटम को unstable कर देते हैं. So what happens in this process? When an electron gets out, we have a vacancy here, and other electrons try to fill this vacancy. So we may receive electron from, so this is K cell, this is L cell. Similarly, we have M cell also. Okay. So electron can come from any cell like L2K or M2K, or let us say electron kick out any electron from L cell. हो सकता है इलेक्ट्रॉन ने L से ही किसी को बाहर निकाल दिया हो. Then electron from M will jump to fill this gap, and in this gap this orbital electron will lose their energy. Why? K cell has the lowest energy, E1. L cell has somewhat high energy, E2. These have E3. So when they come back, I mean when they come to lower energy cell, obviously they will have to radiate their energy. So how much is this energy? This energy appears as X-rays. ये भी X-ray की तरह से appear होगी. कितना energy है इनका? E2. E2 means higher cell, higher level का energy minus E1. So neither E2 depends on incoming electron, ना ही E2 आपके incoming electron depend करता है, ना ही E1. These E2 and E1 are completely coming from the atomic structure of this target atom. What is the corresponding wavelength? This energy is equal to Hc upon lambda. So E2 is fixed, E1 is fixed, H and C are fixed, lambda is fixed. So we get different line at some fixed position, like K alpha line. What is K alpha? When electron jump from L to K cell. We can get K beta line. What is K beta line? When electron jump from M to K cell. We can get similarly K gamma and 2K. We may also get L alpha. L alpha means electron are jumping from M to
M2L.
L beta means N to L. Okay, so this is some nomenclature. But these wavelengths have nothing to do with the incoming electron. Incoming electron की properties से कोई वास्ता नहीं है. This is completely the properties of this atom. That is why we see these spikes at some particular wavelengths only. यही वजह है कि ये spikes आपको मिलती हैं कुछ particular wavelengths पे, and it does not depend on potential and all these things. So these two behavior together gives this complete X-ray profile, and we have some, in some sense we have different origin of these two X-rays. We call them X-ray because both these electromagnetic waves have the same order of wavelength. So these X-rays are in the order of range of angstrom. They also fall in the range of angstrom. So we call them X-ray. Okay. So this is all about this X-ray spectrum.
Sir,
Can we? Yes.
sir, in this graph, some spikes are there, no, sir. Sir, in this, if we keep on decreasing our uh, uh, accelerating voltage of the high beam electrons, then graph will shift left or right, sir?
If you decrease the potential, it means minimum lambda will increase. Lambda increase means energy decrease. So your graph will shift towards right. So I mean in this direction, B is increasing. Okay. In other words, if you apply high potential, you will get lower wavelength. Lower wavelength means you will get high energy X-ray. If you apply lower potential, you will get lower energy X-ray means higher wavelength. So this is B lowest, and that is why you are getting wavelength of higher value, and when you here B is highest, and therefore we are getting lower wavelengths. Okay.
Sir, what can be the lowest lambda?
It depends on applied potential. So this is the
Okay,
lowest value. So it completely depends on what potential did you apply. आपने कितना potential apply किया?
so you mean we can take it close to zero also?
It's not that easy. इतना आसान भी नहीं है. Just calculate how much potential do you need. Figure out कीजिए कितना potential लगेगा आपको. Put
And
desired lambda here. You know all the parameters. Calculate B. And can you generate such a high wave? So with respect to this characteristic spectra, Mosley finds some interesting results. The frequency square root of characteristic X-ray spectra is proportional to or is equal to some A into atomic number of the atom minus B. How do we get this connection? ये connection कहाँ से आया? It is quite easy to find. ये difficult नहीं है. So what is the theory of characteristic spectra? This is for characteristic X-rays. So what is the source of characteristic X-ray? We have two energy levels, E1 and E2. Electrons are jumping from high energy level to lower energy level, and in this process we are getting X-rays of energy E is equal to E2 minus E1 is equal to Sc upon lambda is equal to h nu. And we can calculate E1 and E2. How do we calculate it? Calculate it using Bohr's model. Okay. And what does Bohr's model say? So I'm not going to drive all these things, you know. These energy levels are proportional to what? Atomic number of the nucleus. Okay.
Z square by N square.
Z square and divided by N square also, right? Okay. Or I can say this difference in energy if so E1 is proportional to this, E2 is proportional to Z square upon N2 square, or this E2 minus E1 is obviously proportional to Z square, or this H nu is proportional to Z square, or I can say this nu is equal to nu is proportional to Z square, or root nu, square root of nu proportional to Z, or nu is equal to some constant times Z. This is what I should get. But according to Mosley, it is a slight modification here. Z minus some constant. Or in other words, the effective positive charge which is attracting electron is less than actual value. जो effective charge है, जो electrons को attract करता है, वो actual value से थोड़ा सा कम है. Do you know what is the source of this B?
Sir, characteristic spectrum.
Screening effect.
Yes, this is called shielding or screening effect. Where does it come from? So let me complete this picture. What is happening here? We have a core positive, and around this core we have these cells, okay, and in these cells electrons are moving. Now let us assume a electron is jumping from E3 to E2. मान लेते हैं कि कोई इलेक्ट्रॉन E3 से E2 में जंप कर रहा है. So what are the forces working on this electron? Obviously this positive nuclei is trying to attract these electrons, and we consider this force in the calculation. ये force हमने consider भी किया है in the Bohr's model. But at the same time, this remaining electron cloud, I mean the first cell and the second cell, the electron of first and second cell are repelling these electrons. जो electron first and second cell में है, they will repel the electrons of the third cell. Okay. So the electron in third cell has two forces: attraction due to positive nuclei. It also has repulsion due to cells of level 1 and level 2. So, or I can say that the effective attractive force is less than the theoretical value. जो actual attraction force है, is less than theoretical calculation. Okay. Or I can say that Z, I mean, or in other words, I can say that the effective Z is less than actual Z. आप ऐसा भी मान सकते हैं कि जो पॉजिटिव चार्ज है जो अट्रैक्ट कर रहे हैं उनका इफेक्टिव नंबर एक्चुअल नंबर से कम है, एंड दैट इज व्हाई वी हैव दिस बी हियर. इसी वजह से यहाँ पे बी है. व्हाट इज द पॉसिबल वैल्यू ऑफ बी फॉर के अल्फा लाइन? के अल्फा के लिए बी की पॉसिबल वैल्यू क्या हो सकती है?
Sir, 1.
So K alpha means electrons are jumping from E2 to E1, right? So we have electron here, we have some positive charge here, Z positive charge. We have one or two negative electrons here. So all these positive charges are trying to attract. This electron is trying to repel. Okay, so what is the effective Z? Z minus 1. So B is 1 or nearly equal to 1. For K beta, sorry, L alpha. For L alpha, what is the possible value of B? So L alpha means electrons are jumping from E3 to E2. Okay. So we have attraction of Z positive charges. We also have repulsion of 8 negative charges. So what is the equivalent B? Roughly 8. Experimentally, it is nearly 7.8 or something like that. There are many other factors also. So that's how we calculate B, and therefore we get a slight departures from the Bohr's model. जो Bohr's model predict करता है आपको, उसे थोड़ा सा departure मिलेगा. Okay. So with this, let me end this class here. I'll need one lecture, and this syllabus will be finished then. And
Sir.
let me remind you,
Sir.
it is necessary to submit this assessment test, and deadline is tomorrow. Okay.
Excuse me, sir.
Yes.
Sir, there is one question, question number 10, in which there is finding a dipole moment.
I think that is magnetic moment. I mean, we loosely say magnetic moment also is dipole moment. So it's magnetic moment actually.
Okay, sir.
So the marks of this test will be added in your internal assessment. So please submit it in due time. Only 1 or 2 students have submitted so far. So please, I mean, take it carefully.
We shall do it, sir.